So today I will be discussing about the problems from ideal vapor compression cycle. So number 8, a data center with a cooling load of 100 tons and sensible heat ratio of 0.95. We need to calculate the sensible and latent components. Then we evaluate the risk of over dehumidification if standard VCC system with a lower sensible heat ratio of 0.75 is used. So we have the following givens of Q, cooling load 100 tons, sensible heat ratio of 0.95, then alternative system heat ratio of 0.75. So to find the sensible component, we just multiply the 100 tons to 0.95 and we have the answer of 95 tons. So in our latent heat, 100 tons load is multiplied by 1 minus 0.95, then we have the answer of 5 tons. Now, if we substitute this with the system running at 0.75 sensible heat ratio, it will remove far too much moisture, causing over dehumidification. To find the extra dehumidification load required to restore the room to 50% relative humidity, we take our sensible capacity and look at the ratio discrepancy. My calculation shows that the extra humidification load required 45 tons, multiply the difference, then for the final load is 31.67 tons. And our problem number 9. We are looking at a air handling unit recovery condensate moisture of from 20,000 cubic foot per minute airstream. The air cools from 95 degree Fahrenheit with a humidity ratio of 120 grains per pound to 50 degree Fahrenheit saturated state. So first we must find the recovered gallons per minute and determine if it meets the cooling tower blowdown requirement at a cycle concentration of 4. So we have the following givens of airflow rate V is equal to 20,000 inlet air. Then the humidity ratio 1 is 120 grains per pound and humidity ratio to 64 grains per pound. First, we need to convert the grains pounds to pounds of water per pounds of dry air by dividing 7,000. So W1 is equal to 120 divided 7,000 is equal to 0.01714 pounds per pounds. Then for the W2, 64,000 divided 64 divided 7,000 is equal to 0.00914 pounds per pounds. Now, the delta humidity ratio is, we just need to subtract the two, so we can get the answer of 0.080 pounds per pounds. So plugging these values into our condensate GPM formula, we multiply 20,000 with humidity ratio of delta humidity ratio of 0.080 divided by specific volume of 13.5 multiplied by 8.33. So the answer gives us the 142 GPM for the recovered condensate rate. Then the blowdown now is 4.35 divided by 4 minus 1 is equal to 1.45 GPM. So for number 10, a clean room requires at an air of 70 degree Fahrenheit with 45% humidity ratio. The outside air is at 95 degree Fahrenheit dew bulb temperature and 75 degree Fahrenheit for wet bulb temperature. For first, calculate the VCC load to cool the air to its dew point to remove sufficient moisture. Then calculate the sensible heat. So we have the following givens of temperature 1, 70 degree Fahrenheit with 45% humidity ratio. H1 is 38.6 BTU per hour. Then temperature 2, 95 degree Fahrenheit with 75% wet bulb temperature. H2 of 19.2 BTU per hour. So the delta H here or enthalpy is needed. So we subtract 38.6 minus 19.2. We can get the answer of 19.4 BTU per pound. Then the sensible rate is 0.24 multiplied by delta H, delta T rather, so we can get the answer of 5.28 BTU per pound. So for the reduction, we just divide the sensible rate with delta H multiplied by 1000 to get the rate. So 5.28 divide 19.4 multiplied by 100. The answer now is 27.2. So that is the reduction requires